Hello guys, can you hear me? I need at least 10 viewers to start my it's gone. It's not like because of the background or something, but it's gone. I need at least 10 viewers and more likes to start. Okay. 10 viewers guys, just two more. And like the video. Hello. I'll start. It's three viewers. We need viewers for me to start. Okay, we have good enough viewers now. Right. We have good enough viewers. I know I look weird because you guys are not used to this look, right? That's why it feels weird. But yeah, let's focus on problems. Okay. Let's focus on problems. Let me judge them. Let me give them good. So I think I have downloaded it. I think I have downloaded it. So this might be the PDF. Okay. Can we submit somewhere? Oh, where did it happen? Did it happen in code drills like the video? Like the video? And did it happen in code drills? Like where did the contest happen? Can I give it online? Code Chef. It happened on Code Chef. Really? Damn. I can't see it. Where did that happen, guys? Okay, fine. Seems it is on CodeChef. But yeah, I will explain problems. Mostly if I do it, it's right. It's correct, right? So let's read the problem. Are they in increasing order? I don't see an exam. Okay. See, that's the main difference. In regionals, it won't be like that. Okay. I don't even look good. Like it's nosy shiny somehow. Right. Mm, so let me go and read the problem. A college club is hosting a college club is going to host an ICPC style contest for its. I won't show the chat. Okay, I'll see the chat too. A college club is going to host an ICPC style contest for its college students. Each team participating in the contest should have exactly three participants. Okay, there are n teams participating in the contest. How many participants are there in the total? I think if there are n teams and each of them must have exactly three, it's probably 3 into n is the answer. How? It's just 3 into n. N teams, each of them having 3, 3, 3, n into 3 is the answer. Time limit is 1 second. We have to be quick. Okay, ICPC is not easy. So let me code this in C++. A.cpp. So we have only one integer. We don't need any template. Let me write the problem. N teams, exactly 3 per team. Answer is 3n. So till here, I hope you all of you have solved this. Okay. So let's go to B. Is that fine? Yeah, let's go to B. I mean, I think problems will increase very gradually. You will assume that after this I cannot solve. You should not have such assumptions, okay? I don't know, someone sent me in my group. Let's go to second problem and see how it is. So now we have second problem. Pseudo palindrome. Sounds scary compared to how many, right? But yeah, let's read the problem. You're given an array A of length n and a non-negative integer d. All of this also may seem too much for some people, but yeah, we have to read the problem in a calm and cool way. You're given an array A. I think I might have seen some dates videos, but don't bring that up. I'll remove you otherwise. Uh, is it possible to rearrange A in such a way that is it possible to rearrange A in such a way that you want the first half and you have to rearrange them such a way that first element, last element, adjacent difference should be less than or equals to D, and that should happen for all of them. That is the problem. Okay, just think about it. If n is odd, then what? The middle element can be anything. Okay, but other than the middle element, other than the middle element, you have to you have to pair everything such that all of the pairings is less than or equals to D. Do you see that? Okay, any sort seems a bit more complex. Otherwise, so let's try to see this thing. B dot CPP. Let's see how difficult is this. I hope I can explain well. Okay, we have some conditions. We have to reorder A such that modulus of A minus modulus of A n minus I minus 1 n plus 1 minus I is less than or equals to D. Okay, you have to pair them. What is this? You have to pair them except for middle element if it's odd. Let's look at n even. Okay, if n even, you should pair n by 2. You should form n by 2 pairs such that for each pair this value is less than or equals to D, and you should pair everything. So this is one problem. If n is odd, you keep something at middle and you pair everything else. Okay, so this is our problem. Is it clear, guys, still here? Yeah, it seems clear. So we ES seems a bit more simpler. Let's read the problem again. We have input t-test cases. Sum of n doesn't exist there, so we can do n square. If you see this, we can do n square. Maybe we can brute force. Maybe we can brute force the middle element. Okay. So now, how to solve this one? So you should pair everything. So let's focus on this case because here something at the middle, and then you pair everything else. But here everything. So let's focus on this one. Sort them. Okay, first element gets paired with something, right? What is best? What First element will get paired with something. So when is it possible and when is it not possible? You have to see. You have to try. You have first element. It must get paired with. I don't know. Should we do something greedy? I'm thinking, but I'm not getting anything yet. But let me try to think sometime. You have D. Is it possible to pair these things such a way that, okay, let me just put a weight, an edge. Oh, this seems complicated. Like I'm trying to just, okay, sort them. We have to minimize Okay, we have to pair them such that maximum among these is minimized. Okay, you have to pair them such that maximum among these is minimized. I'm complicating it, but I get it. I'm complicating it, but I get it. This problem has solved in some B, Code Forces B, where they told you have to minimize the maximum of this absolute pairings. There I have seen that best is to sort them and pair a of 0 comma a of 1, and then pair a of 2 comma a of 3, and up to so on. As in that problem I have seen that, like if I want to minimize this thing, you have to pair them, and then you have to, I mean, I'm complicating it, but yeah, there was a Code Forces B problem which I have explained very well in my streams. If you guys see that, I'm complicating it a bit, but there was a div 3b which I explained very well. I think there was long ago a div 3b which I explained well. uh, Long back. 1 minute, 1 minute. I'll just show it to you people. So I will show how similar the problem is. So if you see B, they're telling you to such that maximum difference among the pairing is minimized. You see how common, how similar is this problem to this problem. I mean, we will. I know you people will guess something and submit something, right? I know you people will guess something and submit something, but you see, you have to pair them such that everything less than or equals to D. You have to pair them. You have to pair them such that this difference is minimized. Both are same. Minimize less than or equals to D or minimized or same. But this seems you can just pair AI with the next element. AI, you can pair A0. I mean, both of them are same problems is what I'm telling in some way. Where is the problem? Yeah, if you see this, you have n integers, even. You have to pair them, and then you have to minimize the maximum absolute thing of everything. If that value is less than or equals to D, it's possible, else it's impossible. In this problem, you all have submitted that. In this problem, you all have submitted the greedy way, which is uh, sort them, pair first two things, pair next two things, pair next two things. I have proved very well how this is correct. I have proved very well. I have proved why that's a lower bound, because if you see, if you see first two things, you draw a line in between. Odd number of things, odd number of things. At least one pairing should be here. So this is a lower bound. That's what I have proved. I know I'm complicating it. Do you guys agree that? So for even, pair first two things, pair next two things, pair next two things, and so on. If that value is greater than or equals to minimum, you're good. Else you're bad. See, it's not adjacent distances. Yeah, I will try to. I will, maybe I'll draw somewhere. Uh, See, guys, you have to pay attention to proofs. Okay, it's not easy. I mean, guessing a problem is easy, but then proving it well may not be easy. So what am I saying is you have this n pairs, but it's about pairing first two things, pairing next two things. So it's about pairing first two things, pairing next two things, pairing these two things, and so on. Okay. Why it's not adjacent? It's not adjacent. It's pairing first to pairing next to. How do you prove that this is the best way to get minimum difference? If you are focusing on trying to minimize the absolute value, because for all pairs it should satisfy, right? If you to prove that this is a lower bound, because now we are minimizing the problem, we are trying to find less than or equals to D is the question, which is almost equals to finding minimum distance possible. Okay, because if B is less than the minimum distance possible, the answer is no. If d is greater than or equals to minimum distance possible, the answer is yes. So both problems are almost equivalent. If you guys realize something less than or equals to d, finding the minimum, both are almost equivalent because you can change d to minimum, then its answer is yes. If you change d to minimum minus 1, the answer is no. See how they are equivalent. It's very equivalent. The problems are very equivalent. And if you know minimum is, I hope you guys are getting the logical things. Bro, it's not an easy problem is what I'm trying to show. Like I'm teaching. If I can teach something well on an easy problem, is that a bad thing to do? Just because you guess and submit something and it gets accepted doesn't mean I tell you people this thing. What I tell you people is to solve what you solve well. Okay, if you solve what you solve well, you can improve well. If you don't solve what you solve well, you remain stagnant. Okay, all you have to do is whatever you're doing, do it well. That's all you have to do. Not topics, not courses. Okay, so now, I mean, it's weird, right? It's not adjacent distance. It's like first two things and then next two things. How do you prove that this is the minimum? If you split these two things, these are odd number of things, and then these are odd number of things. At least one pairing should go from here to here. Okay, odd number of things, they cannot be paired among themselves, so at least one pairing will go from here to here. So at least this much is an answer. In this way you can prove that this is in fact, all these things are lower bounds and there is an answer with them. So this is the best way to do. So for even it's done. For odd, what do I do? I will follow the same logic. I will brute force on the middle element. Okay, I'm going a bit quicker. I will brute force on the middle element. Means we have n elements. I will remove that. I will take the other things. I will check if this is less than or equals to d. That's what I do. Okay, that seems easiest for me. Brute force for even. Okay. Int n, c in n. Bool fun. Okay, int fun. It takes an vector int of even numbers. Okay, it takes n equals to a dot size of, this should be even, and then what it does, it returns the minimum distance. What do I do? Sort dot a dot begin of comma a dot end. Okay, and then what do I do? Int d equals to, can n be 1? N can be 1. So I think if n equals to 1, I'll just return true. Wasting time on easy problems, like I know you guys want to know the actual difficult ones, but why not do everything well? Why not solve B well? Okay, so I will just make it like min D. Okay, this is min D. For int I equals to, or I can just make it 0. I need not even write this part. Int I equals to 0, I less than n, I plus equals to 2, min D equals to maximum of min D comma a of I plus 1 minus a of I, and then I'm doing plus 2 if you see, and then if I return this min D, for empty array it will be 0, so we are good. If I'll take an integer array or a vector, okay, now if n remainder 2 equals to 0, answer is fun of a less than or equals to d means yes, else no. Else we can do n square, right? So I will brute force on the middle element. Okay, I'm trying to brute force on the middle element. Let's let that index be I equals to 0, I less than n, I plus plus. I will form vector int b For int j equals to 0, j less than n, j plus plus. I will skip this one. If j not equals to I, b dot push back of a of j, and then I will solve it. Okay. If fun of b greater than or equals less than or equals to d, answer is yes. I don't know how it's an easy problem. I still feel it's not that easy. We can return to. Uh, and then we have to output no else, because now we have brute forced everything. Maybe there is a simpler solution, but this is what I came up with easier. Is this clear? Is this clear so far? Like, okay, now you guys can say, was there an easier solution than brute forcing that and then trying to pair them in a greedy way? Was there an easier solution? But I'm showing how you can prove things. Like, I have proved well, right? I used the fact that this thing is an actual lower bound. Lower bound. All minimization problems are about lower bound, if you guys actually think about them. Okay. Now let's go to uh, see. I use lower bounds idea to solve some 3500 problem. I use same lower bound idea to solve some 2700 problem in contest. So when that idea is right here, you guys will ignore that. Okay, now let's think about this problem. We have C, D, E, F. Yeah, let's see how far I can go. Now we are at C. Okay, we prove very well. Okay, you're given a positive integer C. Don't get scared of anything. XOR is just bitwise XOR is just very small thing. Okay, you have to understand the problem. See, how you have to view the problems is they have some simple proof, logical simple proof. It's not coming up with a procedure. They have competitive programming problems, even ICPC. They are not heuristic problems. They have perfect solution. They have perfect solution, like logical solution. You can say, what this was asked logically, because this was asked, like you can write some, there is the, I mean, there are some logical a implies b implies c, such statements are there, right? I forgot what they are called. They're called something. You can just write them and you can show a clear proof that this works. Okay, problems are like that. So you can see whenever there is LCM and whenever there is XOR, you cannot fit a clear proof using LCM and XOR. LCM number theory is a bit different. It depends on primes, it depends on GCDs. XOR is a bit different. So it's probably brute forcing. They are just messing with you. Uh, I don't mean invariance. What I mean is, see, why I say use invariance is, using invariance is easy to prove things sometimes. But what I mean is, for any problem, there is a clear proof. Okay, logical proof is there. So that when you see XOR together and when you see LCM together, when you see XOR and LCM, they both are not related at all. Like, it's not like you should not think there is something great that involves LCM logic and XOR logic. No, it's probably something brute force. Okay, I know that. Mom said this is good for me. I don't know. Uh, so it's probably something brute force when they say something like that, like maybe this is always bigger than this, maybe this is always bigger than this, and in some extreme cases maybe they both are equal. It's something like that. Okay, so let's see once. uh, you're given a positive integer c. You need to find any two positive integers a and b such that, so you should not get panic. You should write small observations first. I increased brightness, this is max, sorry. So yeah, where are we now? uh yeah, let's try to, it can be proven. See, they themselves are telling proofs are important. It can be proven that it is always possible to find ab's under the given constraints. If c less than or equals to 1e7, it's always possible. Yeah, but you have to think. See, the thing is, you have to make small observations first. If there are multiple possible solutions, you may output any of them. So one thing is clear, guys. A XOR C, LCM, it seems this thing is always bigger than this, but there is some constraint. How much A XOR C can become among A or C? How much big can that become? if you think, it can at max become double. Why? It can at max become double. Okay, why? It can at max become double. Why? The thing is, how you have to solve the problem is you should not think deep. You should make statements from on top of the problem. You should not go deep into anything. You should not stress your mind on test cases. You should not do anything deep. You have to logically see it from above. You have to uh, I think we have to see it from above. If you see that, you can make some small observations in the beginning itself. Some observations you can make is XOR C plus B XOR C equals to LCM of A comma C plus LCM of uh, B comma C. One thing is, logically LCM comma XOR are not related much. So they told it can be proven. So how can the proof come? It cannot come like XOR and LCM will come into one place. But maybe A XOR C is always less than or equals to 2 times of minimum of A comma C or something like that, right? Or 2 times of A or 2 times of A or 2 times of maximum of A comma C. This can be told always. Why? A comma C is just some bits existing, and then again some bits existing. Okay, uh, XORing among them bits. Okay, then maximum. If you take the biggest one, maximum all of them will get activated. Still, it's like less than or equals to 2 times that. But if you see LCM, it is always a big thing. LCM of A comma C equals to is equals to 1 times maximum of that or 2 times maximum of A comma C or something like that. It's multiple of maximum among them. If you see, this is almost always bigger than this is the only observation we need. See the problem. It looks difficult, but if you think, okay, how can there be a simple proof that relates LCM and XOR C, both unrelated things? How can there be a simple proof for this? If you think about that, maybe this is always bigger than this. Maybe if this is always bigger than this, and in some extreme cases they both are equal, then you have your answer, right? But what do they mean? There are always such numbers, it seems, such that x or c plus this equals, you have to find two of them. See, you should not get scared of problem. Maybe 0 comma 0 always works, maybe c comma c always works, we never know, right? So you should never get scared of a problem. Okay, so when when is it uh 1 times maximum of a comma c? When is LCM of a comma c equals to maximum of a comma c? When one divides other. Okay, in all other cases this will be like a bit bigger. I'm still not solving the problem. Let me try to guess something too. I know we should not guess, I say, but then let me try to guess something. Can I make a equals to c and then b equals to x or c or something like that? I'm trying to make one of them as 0. If I make a equals to c, this will be 0, and then this will be a. Some guys, I mean, I'm remembering some comments, some chat comments telling x or c or b or c, but yeah, let me try to solve the problem more correctly. What about c and 2c? Will that work? What about, yeah, C and 2C? Okay, think about this thing. We only want two things. I need not solve the problem at all. Okay, whatever I thought before was wrong, but now I'm thinking, can I make X or C equals to LCM of A comma C? If I think about, I think now I have gotten this. Now I have gotten the solution. If I multiply that with some big 2 power I, if I multiply A, if I make C equals to A times 1 power some 2 power 100 or some 2 power 30 or 2 power 31 or something, 2 power 40 or something. Then what happens? See, you will have C moved that many numbers. Okay, you'll have C move that many numbers, and when you do XOR, you get the 2 power number. But hmm, when you take LCM, then what happens? You get the bigger number. When you take LCM, you get the bigger number. I'm not getting it. Let me try again. Let me try slowly. Should we use two numbers? Should we surely use two numbers? Don't give me any hints, guys. I'll try sometime. Maybe I will get it and then I will go further. Don't give me any hints because we have to see how to solve the problem, right? Let me try to think something because A comma C can be B can be anything. They have many possibilities. If something works, if 0 comma 0 works, then that's the answer, right? If 1 comma 1 works, maybe that's the answer, right? If you make A equals to C, this will become 0, but this will become C. And then you have to deal with a problem where B XOR C equals to C plus LCM of B comma C. Then, okay, that seems simpler, right? Even here I had the even here I had the problem of here I when I do this, what happened was it became when I XOR it became C times it became A plus C. Okay, if you take A equals to this, and if you see C has been moved this much, and then when you XOR A and C, A will appear here. Okay, which is nothing but A XOR C is nothing but A plus C. If you see that, A XOR C equals to A plus C. If A is something very big, of two powers, like you have moved all the A's like here, so you have zeros here. Now you XOR C. This is, and what is this number? This is A plus C, right? A has been moved XOR. So XOR is complex. So what we have done, XOR is complex. So simplify it by moving C so much. So A equals to 2 power 40. The idea is XOR is complex, but you want to preserve information, right? You don't want to lose information. If you XOR two things and information is being lost. So in here, A plus C is possible. You can XOR something and A plus C is possible. Now I can solve the problem. How? So now I will keep A XOR C plus B XOR C, right? I will keep B equals to C. Now what happens? If I keep B equals to C, this will become 0. It will become A XOR C plus 0 equals to LCM of A comma C plus C. Do you see? We were able to make A XOR C as A plus C. In this case, LCM of A comma C equals to A. So in this case, LCM of A comma C equals to A. Why? C divides A. Okay, least common multiple of both of them is that. So this is an answer. So we are using, there are two things. There are two things for us. There are two things to help us, not to make the problem complex. You have to understand everything. There are two things. You can either get scared of them or use them to solve the problem. See the difference very well. Someone might have seen, okay, if there was one thing, it might be simpler, but there are two things that's giving us the freedom. That's giving us the freedom. And LCM is complex, XOR is complex, but when something divides something, then LCM is just max. uh, okay, wait a minute. If this happens here, LCM of a comma c is just max of a comma c, or a. So max is complex, LCM is complex, but our idea is to make them simpler. XOR is complex, but the idea is to move them and then add them. So that XOR, you simplified. If you guys should observe, you simplified XOR to plus. You simplified LCM to max. You solve the problem, but you don't notice all these things because you have a lot of freedom in a comma c. So what is the answer now? A comma c, b, c in a comma b, c out int a equals to c times 2 power 40, let's say, or 2 power 30, let's say. Why 2 power 30? Do you have viewers? And b equals to c. This would work. So this is simply the problem. So a problem implementation can be simple. Like you have to proof is also parallelly done, right? You cannot guess a procedure that works. You cannot guess a brute force procedure. You have to see the problem for what it is. The problem has that it is possible to prove. If you're ignoring this thing, you're throwing the problem away, right? You cannot ignore that it's possible to prove. So let me go to D. Is this clear? Is this good explanation? So but I am telling you people that it comes from proofs. You have to believe that there is a proof. You have to work in a logical way, not in a procedural way, like I told this in my previous stream too. Okay, so this is a good problem because okay, you can get to work, you can try to think something, and then you have to come up with the solution. Okay, they can be smaller too, but this is a simpler thing that works all the time, right? Am I correct? Okay, I have one doubt. Am I even correct? I will just verify them very clearly. A XOR c here is a plus c. B XOR c here is 0. Very clear. That's very clear. Equals to LCM of a comma c here is a plus LCM of b comma c here is c. A plus c equals to a plus c. I'm good. I think that's a clear, correct solution. So let me go to D and read the problem. They all appear scary, but we should not get scared at all. We don't know. See, even E may not be that difficult. We should not get scared. Okay. Let me go to E and then come back to D. Okay, because I'm good at counting, and you guys will be scared of E, right? Or maybe you guys will be scared of F, right? So let me go to E and then come back to D. Okay. I'm just thinking people will drop or something like that. Yeah, that's what I have done. It's correct. So yeah, E. You're given a tree with n nodes and a positive integer c. So we should not get scared of tree. We should not get scared of any problem. We have to read the problem because that's what helps us solve the problem. So you should not get scared of problem at all. The ith edge connects the nodes ui and vi. So we have a tree. Before the traversal begins, you must choose a permutation and label the ith edge pi. Before traversal, you have to choose a permutation and you have to this is nothing but there is an ordering among edges. Before the traversal begins, you have to say okay, this is the first edge, this is the second edge, this is the third edge. So that's what we have to do. These labels remain fixed throughout the traversal, and those labels remain fixed, it seems. You start from node 1 with integer x equals to 1. So you start from node 1 with, you have an integer x equals to 1. During the traversal, you can perform one of the following operations. Traverse an edge adjacent to your current node. If it is, see, when there is something to work on the problem, you have to be happy about that. You have to see, okay, I can try to work something in here. Okay, I will come back to fourth, but let's focus on this one when I'm explaining. Okay. So yeah, uh, yeah, can't you do that simple task well, Rudra? Operation A, traverse an edge adjacent. Okay, so when we are during the traversal, we can do two operations. It seems traverse an edge adjacent to your current node if it is not labeled with x. So we have a number x, and we can go to we can traverse an edge if it is not having our number x. After traversing, you move to the node on the other end of that edge. So you traverse if it is not labeled with x, increment x by 1. So this is our traversal. You can either do this or you can either do this, and once you increase, you can never reduce. You must start at node 1, visit all nodes, and return to node 1. The cost of traversal is the number of times you perform operation B. Okay, we have to start at here, we have to touch everything, we have to touch every node, and then we have to come back to 1. The cost of traversal is the number of times you perform operation B. Define f of, okay, this says something. This also can be worked upon. You have to, this is the cost. Define f of p as the minimum cost of a traversal when the edges are labeled according to permutation p. Your task is to count the number of permutations such that f of p equals to c. Since the answer might be large, output it modulo something. So the problem has too many things. But if there are too many things, that's good for you, because if you're willing to put work, you can solve the problem when there are too many things, right? It's not like someone gets the solution right away. You have to, if there are too many things, that's nice. So let's simplify the problem as much as we can. So we have f of p, minimum cost to traverse everything. Okay, you should find number of p such that f of p equals to c. So what is the first step you should do? Work on f of p. Okay, what is f of p? You have to work on that, and then you have to think of, okay, how to now compute. So you have to make f of p equals to, you have to work on f of p, and then you have to make f of p equals to c, implies some conditions. Okay, and then you compute such p, and then you will try to count them. So first you have to simplify that. First you have to work on f of p. What would be f of p? You have to work on that. Okay, so if you try to see, if you number of operations b is, what is the final value of x, right? What is the final value of x is number of uh, this number exactly. Okay, so this seems, if one is at the end, let's just think about one test case. Let's say, uh, so the thing is, see, you cannot traverse an edge. It's a tree, right? It's a tree, right? You cannot travel. I mean, can you keep one and traverse everything? There is an edge where one exists. There you cannot cross that. Can you make the traversal with one, with x equals to one? No, you cannot cross edge one. You cannot cross the edge that has weight one. So that's the problem. You can traverse all of them. Okay, you can traverse all of them. You have edge 1 here, you can traverse all of them without this one. You can traverse all of them without this one. So if you have x, if you have value x, that splits the tree into two subtrees. So whenever you are having a value x, what does it do? It splits the subtree into this and this. All of this, if you're here, all of them are covered already. You need not worry about them. If you're here, but then you cannot cross this thing. So you must do something x plus 1 if you're at x to go to this subtree. So those things you can just say, some simple things you can just say. Okay. So with x equals to 1 itself, all of them are touched. Now you need not touch them again. See, now only you have to go from here to here. All of them are touched. So you have to see the problem well. It's ye. Why do we not have any viewers? 11. See, I'm not just explaining problems, I'm live solving them. People don't get it somehow. It's even more precious than just some solutions, right? So if you see one, edge one, all of these things can be traversed. Okay, now we have to make it two to cross and go here. We have to come back to one, but let's think about that. You have to come back to one. Okay, what I'm saying is, let's this be x, okay, current x, and then you have a subtree here, and then you have a subtree here. If you're here, you can touch all of them, you can cover all of them now itself, but then you have to make it x plus 1 to go from here to here. So can you somehow write f of p in a nicer way, that you have to come back? So once you cross here again, you can come back for sure. Why? Because probably because you might have been greater than x, right? Sorry, uh, even if it is less than x, you can cover all of them. When you are at x, you cannot cross this. That's the only thing, right? So let's just see. Let's see one edge 1 and edge 2. Okay, let's see, we have edge 1 here and edge 2 here. Can we always do it with three edges? Maybe that's possible, we never know. Maybe it's always possible with three edges. It seems like that, right? Because x, all of them are connected, all of them are connected. So you have to you cannot think it involves something big unless you solve the problem. Maybe it's always c less than or equals to 3. Maybe it is. uh, Otherwise 0, still the problem can be difficult. Even if c less than or equals to 2, otherwise 0, even then the problem can be difficult. Okay, so because you have to count again. So when problems appear difficult, all it takes is to solve the problem. Let's say h1 is somewhere and h2 is somewhere. So now you have this subtree, and then you have this subtree. You can, and then you have this subtree, and then you have this subtree. Okay, so let's look at edge 1, edge 2. Let's look at the path between them. Okay, let's look at the path between them. So you have this subtree here, you have this subtree here. Okay, these are edge 1 and edge 2. So if you have one on this side, you can cover all of them with one itself, and then you make it two, let's say, and then you can cover all of these things, and then you can cover all of these things too, and then you come here. So 1 2 was done. So and then you have to see again 3 might divide it. So to understand the complexity of the problem, if you see this particular test case or this particular graph, where you have 1, where you have 2, where you have 3, where you have 4, 5, up to so on. If you are here, there is no way but you have to increase it to cross this. You have to increase it to cross this. You have to increase it to cross this, up to so on. You have to increase everything, and then you go here to n. To touch this, you must increase that from 5, and then it will become 6, and then you can come back. So in some cases it's not less than or equals to 3. So in this case itself, it can always be 6. Okay, so you have to think again. So what is this value? Is it like somewhere 1 here, somewhere 2 here, somewhere 3 here. Like they're forming some perfect cuts, right? Like something like this itself. If you can form 1, if you can form 2, and if you can form 3 in a path, if you can form 4 in a path, is this a lower bound? It's a minimization problem. So we have to look for lower bounds in a minimization problem always. The same B, same E. Uh, Minimization problems, you have to look for lower bounds to prove that it's minimum, okay? So now, let's say something like this existed. 1, 2, 3, 4 existed, let's say, okay? If 1, 2, 3, 4 existed as a path, if there is a path from 1, 2, 3 up to so on 4, and 1 is here, to cross this one, you must make it 2. And to cross this 2, after that, if 1 is here, see, you cannot come with 1 here because 1 is before that, right? And initial 1 is here. So this is a lower bound. A path of edges, a path, any lower bounds for f of p, a path of edges 1, 2 up to so on c is a lower bound. Do you guys see how I'm writing, how I wrote one lower bound already? And you know why lower bounds are good? If you have a test case that matches a lower bound, then that's the answer. If you have a test case where 1, 2, 3 up to so on c, if this was the permutation and you have some extra things, at least this must be done. So lower bounds are very important because they will not lead you go in wrong direction. If you try some procedure, it is coming from this side, you cannot know how close you get. But if you're coming from this side, from lower bounds, you can write a test case where your lower bound is the answer, and in that case you have to be doing this. So finding lower bounds is already always safe option, okay? So maybe, so now I have to think, is this the lower bound? Is this the lower bound? What if 1 is not here? What if 1 is not here? What if 1 is somewhere else? Okay, we have 1 here, right? We have 1 here. Let's say the initial node 1 is here. Initial node 1 is here, let's say. But then you have to come back. That makes the problem more complex. Fine, fair enough. We have to come back. That makes it even more complex. A bit more complex. And return to node 1. But it's complex or not will solve the problem. Okay. What I mean is, while coming back to 1, what if there is c plus 1 in between? Then you have to again increase that, right? So let's say there is a path. Okay, there is a path 1. There is a path that has 1, there is a path that has 2, there is a path that has up to so on c. And then the same path had c plus 1 here, and then c plus 2 here. Is that a lower bound? Think about that. Is this thing a lower bound? See, c plus 2 here and c plus 1 here is failing, because once you come c to c plus 1, c plus 2 will never come. So it's like coming till c plus 1, because and then you can make it c plus 2 and then you can go back for sure. So is this thing a lower bound? So you have 1 somewhere here, okay, the start, and from the start at some point you cross the node 1, the edge 1, and then you cross the edge 2, and then you cross the edge 3, okay. And then while coming back, maybe there was some 4 here, maybe there was some 5 here, after this 3 has been crossed on the same path, not even here, because you need not touch if it was here, right? You can just come back because all of them has been traversed. You can just come back. So this seems to be a lower bound. 4, 5, 6 before this one. So if there is a path of node 1 and then edge 1 and then edge 2 and then edge 3, and then while coming back on the same path, edge 4, edge 5. So this is the answer. So now we have our answer. For given a permutation, we have our answer. Maybe this would be the answer, right? Find edge 1, find edge 2, find edge 3, up to so on, as long as they are in a path. Okay. What if 3, what if they don't form a path? What if 4, after you come here, what if 4 doesn't lie on the same path, but 4 lies somewhere here? Then you're done. You solve the problem probably. 1 minute. Then you can come back. Then you can come back. Oh yeah, then you're done. Why? You might have touched all of them. You might have touched all of them. You might have touched all of them before itself, right? And then you will come to 3. You will make it 4. You can go back. So see, this is precisely the answer. Do you guys see how a simple structure is precisely the answer? But do you guys see how we have solved this problem so well? So it's about existence of this path. So we have node 1, okay, and then uh, edge 1 is here, let's say, and then edge 2 is here, let's say. If something is not on the path, if something is not on the path, if somewhere here, then this is the answer. You went to 2, you came back. That's the answer. Why? When before crossing this itself, you might have visited all of them, right? Before crossing this 2, the value is 2, and then you cross 2 by making it 3, and then you just come back to 1. You can touch everything too. So do you see how logically good this problem is? Do you guys see how logically good this problem is? So see, the structure is not too complex. From node 1, you have this edge 1, and then you have this edge 2, and then you have this edge 3, up to so on. And sometime they may fall back on the same path. Okay, 4. But if they don't fall on the same path, if they are not falling on this side, if they're falling somewhere here, then the problem is done. This is the answer. Else, if they're falling on back, then again they will contribute to the lower bound. Okay, because you have to come back to 1, and then if they're falling 5, and then if 6 was here, then 7 would be the answer. So if you see the structure, it's like only one path is being important for us. There is one important path for us, like till here you come, and then after this 3, 4 doesn't fall on this side, 4 falls on this side. So 4 falls on this side. So because C is fixed, maybe we can solve this problem in some way. So maybe you can brute force the property of this node, which is of till here you come, and then here it will be 3 or something, and then you will have 1, 2, up to so on, some z till here, and then z plus 1 will be on this side. If z plus 1 is on this side, you know exactly, if C is the answer, C should be c minus 1 should be on this path itself. Either c minus 1 ends here or c minus 1 ends here, and then you have to place, and then you have to place 1 2 up to so on z in increasing order, and then you have to place z plus 1 z plus 2 up to so on c minus 1 in reverse order. So you have to just place something like this. You have to place something like this on one path. So this seems can be computed, right? You're brute forcing on this node where you're returning back. You're brute forcing on this node where you are returning back in terms of our optimal path. Do you guys see how I'm solving the problem? It's premium content. You guys can never get such good explanations on live. I don't know why no one's replying at all. I get that. So is anyone following? Mohit, were you able to follow this one? Like, I really want to test this solution. Don't they provide judge for us? Okay, but do you guys see now? Now this is the low. This is a lower bound, and this is the answer. This is the answer. If c plus one, if after three, four goes somewhere here, four is the answer, because four is a lower bound and four is the answer. So the structure is from one you have a path, one two up to so on. So the structure is from node one, you go to a vertex. Okay, that vertex will be have z until here. Edge one will be here, edge two will be here, up to so on edge z will be here, and edge z plus 1 will be here in the behind, up to so on c minus 1 will be here. So how do you count such things? This is a lower bound and this must be the lower bound. If any of them misses somewhere, you can do less than c. Why? If after z, if z was somewhere in the behind, you can come back. Of immediately after 2, you can come back, because you can cover all of them, because z is not here, 3 is not here, 3 is here, and then you can come back and the problem is done. While going, you covered all of them, and then you come back to 1. So this is precisely what is, see, minimization problems, it's all about lower bounds. So guys, do you see this structure is a very good lower bound? And if you see, how many edges are we selecting here? Let's fix this path, node V. What is this node V? Where the lower bound path is retrieving back is node V. Okay, where the lower bound path, I think at least I can test samples, maybe stress test. So I will brute force this path V. So if the number of edges here is m, we have to choose how many edges among them. C minus 1 edges should be 1, 2, 3 up to so on C minus 1. And there are two colors among them. Two colors. What are those two colors? So this color is always green. Let's say the forward edges are colored green. Okay. And the backward edges were colored red. So now you have M colored edges on this thing. Okay. And this part is green. Okay. Because that is both forward and backward. So this is forward. This part is green. So now you have M edges here. You have to, this is green already. And for the remaining things, you have to color them either green or red. If you color green, what does that mean? One starts from the first green, 2, 3 up to so on. So we are not fixing Z. We are trying to color, we are trying to see it in a general way. Okay, do you guys see how I'm doing that? Is anyone understanding? Is anyone, at least one person, is able to follow? Even though these are very good explanations. Yeah, see, so these are combinatorics ideas. We have to find a structure. You cannot do in O of n square. You have to do in O of n. You're brute forcing V already. You cannot brute force Z again. So how can you see that in a nicer way? Number of edges is fixed, but number of forward and backward, they are adjusting, right? So we have C minus 1 colors. One of them is already colored green, let's say. And all the other things can be colored in 2 power C minus 1 ways. It's choosing a subset and making it green, right? 2 power C minus 2 ways, you can color all of them. And if you color all of them in 2 power C minus 2 ways, for each of them there is a bijection of a path. Okay, what is the bijection? Take any green coloring and remaining red coloring. The first green coloring will be 1. The next green coloring will be 2. Up to so on, this Z you come, whatever the number of green edges are, that will be the Z. And then you go back. Z plus 1 will be on the red edge. Z plus 2 will be on the other red edge. So now you have colored. So now let me write well. So can be counted and return path. So what is the lower bound? 1, 2, up to so on C, up to so on Z, Z plus 1, Z plus 2, up to so on C minus 1. C minus 1 can be occurring anywhere, but they should be occurring in this increasing order. So the structure itself makes it simple to count for us because it's increasing and decreasing. So this order is already fixed. It's about just choosing them as red edges. Then the number will be fixed. If you choose green edges and red edges, then the numbering is fixed. Z will be fixed because of them. Because one node 1, okay, because the edge 1 will go here, edge 2 will go here, up to so on. The green edges will become that, and then you come back. So brute force can be counted. Brute force the node where Z occurs. So we are brute forcing this node V where Z occurs. If you see from node 1 to here, you cover all of them and then you go here. And then you make it 2. Cover all of them and then you go to 2. And then you cross 2. You cover all of them and then you come here. You make it Z plus 1 and then you cover all of them. And then you come back. But then again Z plus 1 is causing the problem. You have to make Z plus 2 to cross that. All of them are already covered. No need to worry about them. And then you must cross Z plus 2. And then you must cross Z plus 3. So this is a lower bound. And this lower bound is enough. If this is the if this is the lower, this is a lower bound, and if Z plus 3 is somewhere else, you can come back. That won't cause you a problem. I mean, if C is somewhere else. So now you have to select, let's say you have M edges. You have to select C minus 1 edges, okay, and color C minus 2 edges either red or green. Why? The last edge is already colored green. That doesn't have a choice because you're already brute forcing on that, right? You're already brute forcing on that. So what is the answer now? So you can color them in 2 power C minus 2 ways. So M greater than or equals to C minus 2. This is a necessary condition first. Okay, M greater than or equals to C minus 1 because all 1 to C minus 1 must fall on that path, right? So M is greater than or equals to C minus 1. And then 2 power C minus 2. What if C equals to 1 or something? If C equals to 1, it's impossible, right? C1 is impossible. Why? You have to cross the edge 1, then you make it 2, and then you come back. So C equals to 1 is impossible. Anyways, we need not worry about that. C equals to 1, the answer is 0. So we solve the problem. Solution won't be difficult. Solution will be easy. So 2 power C minus 2 is the number of ways you fix the Z and then you can come back. What are remaining edges? they are n minus 1 total edges minus c minus 1, because you are painting c minus 1 edges in this process, right? And they can be of any order. They can be of any ordering, it doesn't matter. So the answer is 2 power c minus 2 times factorial of n minus 1 minus of c minus 1. So this is the answer whenever m is greater than or equals to c minus 1. But it's not done yet. You have to choose among these m minus 1 edges, you have to choose c minus 2 edges. That would be m minus 1 c minus 1. So okay, we are coloring them as red or green, but first you have to choose them, right? First you have to choose them too. So what I mean is, what are the edges that are being colored? First you choose them, that is m minus 1 c minus 1. Okay, you're choosing among these m minus 1 edges, these total are m. If you remove this m minus 1, you have to choose c minus 2 things among them, okay, because this is already chosen. So you're choosing c minus 2 edges, and then yeah, you're first choosing c minus 2 edges, and then you're coloring them as red or green. Okay, this edge is already chosen. You're choosing because there are more edges. You can choose any of them. The only condition is one should occur before 2 up to so on z, and then you have to come back. Because you have to go and come back, we are coloring them as red and green to indicate the number, to fix the number. So first I'm choosing, the last one is chosen because this has been brute forced. We are choosing m minus 1 c minus 2 edges. After choosing them, coloring them as red or green, 2 power c minus 2. And now you have your answer path. And the remaining things can be like that. So this is the answer. This we brute force for all nodes where m is greater than or equals to c minus 1. So m is greater than or equals to c minus 1 is being taken care of NCR. If you see, if m less than, this value will become 0. Okay. So now how do I code this quick? So because in ICPC you don't have template, right? You have to write everything. So I'll write everything quick. Okay. And then if samples passes, mostly it will pass. Okay, I'll try to code that too. Do you guys understood this problem? Does this use topics or lower bound? Yeah, it uses the lower bound I told. I mean, some combinatorics which I use very easily might not be that easy to understand, because you have to see the bijection easily. Okay, some nodes are being selected. So m minus 1 c minus 2, because the last node is already brute force and is selected. Among them, some are forward nodes and then some are backward nodes. So that's why 2 power c minus 2. And now, what about the remaining edges? They can be numbered in any way possible, which is factorial of that one. So if I submit this, so implementation is simple again, except for the factorial. I'm trying to write some code. Other than that, implementation is simple. So I will write the whole code. I mean, always that if combinatorics appears difficult, the thing is, combinatorics is never difficult in general. I mean, if you do with clarity, it's not difficult. Okay, so I'm writing power function. This is like binary exponentation, which is nothing but, if you want to power 2 power 100, it's first better to power 2 power 50 and then just multiply that twice, square that. Y reminder 2, we multiply. If it's 2 power 101, first multiply that, make it even, and then divide. That's the idea. Okay, so this is squaring part. This is odd part. I make it like that, and then I'm squaring it, and then I will make the exponent by 2, and then I return rest. So this is binary exponentation. Okay, and now we will also form factorial. So see, this structure is a lower bound. The structure of Z, stopping at Z and then Z plus 1 occurs on the same path but behind. This is a lower bound because after you cross this Z, the value is Z plus 1. And then all of them can be touched already. Okay. So this structure is a lower bound and we are brute forcing that structure. So given any tree, the structure should be like, why are we coming back is because Z plus 1 is on this side. Okay, Z plus 1 is on here, we go there. But Z plus 1 is on this side and it should not be somewhere here because then the answer won't be C. If Z plus 1 is somewhere here, we can just come back with Z plus 1. So Z plus 1 is here, Z plus 2 is here, C until C minus 1 are here. That's why we have to make it C and then we return. So first I made it very clear what is f of p. F of p is if f of p equals to C, that means 1, 2, 3 up to so on some Z, there is a path. And then Z plus 1 is in the reverse path and then Z plus 2 is in the reverse path up to so on C minus 1 or in that increasing path. Only then the answer is C. Otherwise the answer is not C. If this structure exists in the tree, then the answer is C. Edges are not fixed yet. What do you mean edges are fixed, right? Edges are fixed. Pawn of the board never misses hard coder. Did anyone understood? I think if Mohita was there, he would have understood. I mean, Mohit also would have understood, but he's telling something is not. What about Badri? He says he sees. Okay, I like the problem anyway because it's like good idea of lower bounds, right? So do you mean why am I telling to come back is we are trying to see what it means that f of p is C. That's the problem, right? What it means that f of p equals to C means 1, 2 up to so on Z you went and then Z plus 1 up to so on C minus 1 fall on the behind. It could have been 1, 2 up to so on C minus 1. Even then the answer is, and then what the, wait a minute. And then there is more to this problem. C should not fall on this path. C should not fall on this path. That is another constraint. Damn. It's a good problem. I would have enjoyed it if I solved it in some C code forces round. And C, because otherwise you're not brute forcing it, right? Otherwise, if C falls here, you're not brute forcing on C perfectly. And C should not fall on this path. On this path. Okay. So C should not fall on this path. So now, what are the possibilities for C? What are the possibilities for C? C will be in other edges, which is n minus 1 minus of m. Total edges are n minus 1. You have m edges here, m edges here. If you remove these edges, these many edges will be for C. It's all multiplication principle. You have to get better at it. So C will go into one of them. Then all the remaining things can factorial themselves. All the remaining things can rearrange as they want. C chosen this one. So C is also fixed now. We've kept everything till C minus 1. We kept C somewhere else so that the answer is C. So the structure for answer to be C is you keep C minus 1 till here and then C should be somewhere here. C should not be on this path. Then the answer is C. That's the structure of the problem. That's the structure of the problem. So minus 1. So this would be the perfect answer. Define n. See, we have to be very careful in counting. Combinatorics is easy, but then if you cannot debug that, it's all about getting good. It's not about getting good ideas, but doing good work. All I need is height, which can be passed like this. Okay, height will give me number of edges. So now I solve the problem. Let me make fact. Let me make inverse fact 2. Let me make a function called NCR. If r less than 0 or r greater than n, return 0. else answer equals to factorial of n times inverse fact of r. Answer times equals to inverse fact of n minus r. Answer remainder equals to m. Written answer. We have our ends here. We have to make factorials. Fact of 0 equals to in ICPC regionals you must have to write all the code by yourself. You cannot copy paste templates. Writing code is not that difficult. See, I'm writing. I have to write mod inverse. With Fenwick's theorem, with Fenwick's with not Fer, with Fermat's theorem, we have a power m minus 1 equals to 1 mod m. To find a inverse, we do a power m minus 2. So we have everything. So now we are here. What is m? Int m equals to just h, right? Okay. Now what is answer? I'll just take the pre-input. Pushing the edges. That's it, the problem. Now we have to work on here. We have to just put our formula from above to here. We need 2 power c minus 2, 2. So I'll start from here. So I'll start with NC, choosing c minus 2 edges. Okay, one edge is already chosen. Int pos equals to, first choose m minus 1 c, choose c minus 2 edges. Okay. Let me keep n2 here. Choose c minus 2 edges. Okay. Now among them color them red and green, which is 2 power, we are not coloring the last one, which is 2 power c minus 2. Okay, so now these two parts are done. Now we have to choose this one, n minus 1 minus m. See, if there is no space, if there was no space, it might have gotten already 0. Okay, so this makes sure that there was space for c minus 2 edges. Okay, now if you think about it, why is c n minus 1? C can be n minus C can be n, right? Some cases. Because if there is 1, 2 up to so on n minus 1, you go plus 2, 3 up to so on n, and then you come back. C should be less than or equals to n. I don't know why they made that mistake. C should be less than or equals to 1. Sometimes it can be n2. Okay, they made this for our use case maybe, because now we have c minus 1 edges here, which is n minus 2. Okay, this they gave us for our use case. If c is less than or equals to this, wait, there are only n minus 1 edges. C can never be n. C can be n sometimes, but I don't know why they haven't given that. C can be n. So factorial of n minus 1 minus m is what we do. N times n minus 1 minus m. So this will make sure that m is greater than or equals to c minus 1. This will make sure that m greater than or equals to c minus 1. Otherwise it will be 0. So because m is greater than or equals to c minus 1, okay, among the remaining edges, you should be able to find this. If the remaining edges are 0, this will become 0. If the remaining edges are negative, that's not possible. Why? Can the remaining edges be negative? No, the remaining edges won't be negative. These are the remaining edges. If they are 0, this value is 0. So that's clear. N minus 1 minus m is always clear. So I just have to multiply that with that. N minus m minus 1. So total edges minus edges on the path, remaining edges. Was remainder equals to m. So now you can refactor everything as you like. Factorial of n minus 1 minus c minus 1 minus 1. Okay, now c edges are colored. Okay, you have colored c edges. You have colored c edges. So now, what are the remaining things? N minus 1 minus c. These are the remaining things, right? Sorry, minus 1. Yeah. This will become minus c plus 1 and then minus 1. Answer plus equals to pos. Answer remainder equals to m. And then we are done. We are good. This just finds path. Problem is done. So let's just test this one. So now let me test the test cases. So let's check the first test case. C is 1, N is 2. So this would be the one test case, right? For suspense, I'm adding them like that. What happened? Why is there no answer? How can DFS go on forever? I'm clearing it. I'm pushing right. Maybe power is written wrong. Do you guys see some error? Hi, for the hello. So I explained E very well. Maybe check out later. Okay. Yeah, I don't have that much rating, but yeah. Asphalt 8, you might have liked the E problem, but came late. I don't know those things. I'm explaining E, which is very difficult and nice. Good combinatorics was there in E. I answered you right now, Ravi. Okay, you guys are waiting for D, but how is E? Let me debug this. Like, what's happening here? Why is it like going forever? It should not, right? Let me just remove these things. Keep the simplest DF as possible. Okay, they have some error. What issue can they have? Okay, uh, okay. If m equals to 1 seems an issue. If m, I think m minus 1 should be positive. Okay, otherwise it doesn't make sense. Not m minus 1. M minus 1 should be greater than or equals to 0. I think that's the only case where it's going wrong, because in this case r is, I think n negative also should be handled by this. Okay, okay, in this case n is, r is positive, r is greater than n, so it will return 0. So this, I know this function is good function. How is this going wrong? I'll just remove the power and just check it. Okay, even now it's working. So the only thing that's going wrong is the power function that I wrote. So I checked that, right? What can go wrong here? While why is this taking an infinite loop? That can take an infinite loop. Y by 2 is happening, right? Okay, what if y is negative? Fuck, I see it now. I thought if y is negative, whatever the value written by this, it's fine, I thought. Damn, this, I think I should be careful in real life. Even in my contest, I should be careful about this. So now it's right. It's perfect. Perfect solution question, but then the answer says 0. So let's verify that. What went wrong? Okay, let's see test cases. Oh, that's fine. Once it becomes 0, it comes down. It's not a recursive function, it's iterative function, okay? There can be a recursive approach, but this is iterative function, okay? Uh, so you were right here by telling Pradeep, but it's an iterative function, whatever I wrote is. So let's see. Let's look at test cases. What is the answer for that? Answer for that is 1, but we are telling 2. Why? How can C be 1? How can C be 1? You will label 1 comma 2 as 1, right? Okay, but you will label 1 comma 2 as 1, right? How can C be 1? Okay, okay. C is C minus minus C. C is the cost, not the final value. So C is the cost taken. So we are reaching C plus 1. means we are reaching C plus 1. That's what I was confused about. Why is C less than or equals to n, right? So the C I am seeing is C cost. C cost means 1 plus C is the final value. So that's why C less than or equals to this. I thought C less than or I thought C should be between 2 and n, right? Yeah. So it is C plus 1. I think if I just do C plus plus, it will be fine for my understanding. So we should do C plus plus because our understanding of C is not the cost but the final value, right? See, now we should be getting one. Now we should be getting one. Now let's just verify that. So C is 2. Okay. We are here. Here it's 0. That's fine. And now here we are. 1, 2. We are fixing this one. M minus 1 is 0. C minus 2 is 0. Okay. 0 of 0 will be 1. Okay. C minus 2 is 0. Again 1. Okay. And then n minus 1 is 1. Okay. Okay. If it is. Okay, I get it. In our case, the C plus 1 edge or the C edge, it should be outside. If there are no outside edges, that's also fine. Also, that is fine. C should be outside. If there are no outside edges, that's also fine. The only condition is C should not be inside. Okay, I'm trying to. If C cannot, I thought C must be placed. So, how to update this to that? If outside edges are 0, then it is 1 because you're fine already, right? And then, okay, so because of C plus 1, this can be negative sometimes. So we have to deal with C equals to n case. Only case that's troubling us is C equals to n. 1 minute, we have to be very careful. Okay, it's not outside edges equals to 0. It's not outside edges equals to 0. Okay, it's not outside edges equals to 0. We have to be careful here. I think everything is fine. Just because now C can be equals to n, we are facing the issue. Because before I thought C cannot be equals to n. So I have to only deal with C equals to n case. Okay. If C equals to n, else I think this works. Because if C not equals to n, then C will be less than or equals to n minus 1 and it will go somewhere and that somewhere should be outside. So this is right. But if C equals to n, C can not be anywhere. C won't be anywhere. It's fine. C won't be anywhere. You need not do anything. If C equals to n, you need not do anything. It won't occur. 1 to n minus 1 are the numbers, right? So it won't occur. See, it happened only because I have seen the cases. I haven't seen that C equals to n possible. That's why I have seen these things very well. But now we have to say if C equals to n what? If C equals to n, this is just remaining things factorial, right? So I will keep this also inside. If C equals to n, what about this thing? You have placed everything on the path. C equals to n. I have placed everything till here. C equals to N. You're placing C edges. All of them have been C minus 1 have been placed here. You need not do anything. You can leave right there. If C equals to N. It's 1. If C equals to N, you have placed all of them here and then you're done. N will go outside, N is not there, nothing else is there. But if C is less than 1, among the remaining edges, you reorder them. You must place C somewhere. You will place C somewhere. I'm not hard coding, guys. So this was one. So now let's verify the final test case. 5 and 3. This is the final test case. This was 0. Now let's verify the in between one. So let's see 1 2, 1 3, 1 4, 1 5. And the value is 1. In our case, the C is 2. Means you can place 1 here or 1 here or 1 here or 1 here. So the number of possibilities is 4. The answer is 4. Okay. After you chose that any of that 4, you can rearrange other things as you like. 4 edges, 4 factorial is the answer. 5 1 1 2 1 3 1 4 1 5. See 24. We can test some other cases too if our solution is correct or not, but I think it's perfect. So how to test this code now? See, code is simple again. Code is simple, but it's not easy to come up with. Not It's like coming up with this lower bound is not easy, but it's quite high because if you try for lower bounds it's easy, but you guys won't try for lower bounds, right? So now let me go back to D. See, it was all about lower bound. You have to find a lower bound. Okay, if 1 2 3 are in a path, that's a lower bound. Okay, now we have to extend it 1 2 3 up to so on reverse. If all of them are in the reverse path, then this is a lower bound and that's a good enough lower bound, and then the problem is done. You guys see, do you guys see how lower bounds are coming into picture and how I am able to solve live on stream without any fear? So now let me go back to D. Oh, D is also a permutation. There is some permutation it seems, but yeah. So now will I get scared of D? I was able to solve E without any fear, right? Will I get scared of D? I don't think anyone else is doing E problem on stream live, but you guys, no viewers at all. You're given a permutation, it is guaranteed that n is even. You can perform the following operation on it. Select a subsequence of length 2k such that either we have to select a subsequent 2k elements such that either maximum of either first half is less than second half, or what is a subsequence? Should the first thing should be before, I mean, should tk less than tk plus 1? Maximum of this less than minimum of that means either all of them are above this or all of them are below that. Okay. So we have to select two groups such that one group is entirely above other group. Okay. You want to make P empty using minimum number of operations. You can perform the following operation on it. Okay. What can we do? Okay, these are indices, are they? Subsequence. Okay, what is a subsequence? Okay, it's like sequence. Okay, it's like a sequence of 2k numbers. Okay, it's a subsequence. Why didn't they say subsequence of P? Let me try. Let me try. But don't spoil the problem for me, okay? K need not be same across operations. It seems you must also print the subsequences used in minimum number of operations. Okay, it's like a good problem again. So someone is telling answer will be 1 or 2. Let me think about that. You have to choose two subsequences such that You have to choose two subsequences such that either all of them are below or all of these are below. All of these are below or all of these are below. I don't think it can be done in two operations. How? It can be in any way, right? How can you do it in one operation? It's either like this or like this. Only then you can do it in one operation. Okay, but let me try the problem, right? If I have solved E, this should not be easy. See, it's again minimization problem. It's about lower bounds. You guys will never learn, even though I stress it a lot. Some guy is calling me. I don't have time. I don't know. I prefer text, I guess. I don't know which H1 this it is to. See, we have to try for lower bounds. The operation is clear. You have to think about the operation. You have to say some lower bound. So someone is telling answer is always one or two, but I doubt it. It's like lower bounds means, see, all minimization problems are finding lower bounds. You will define something and you show that this is a lower bound, and because of that you prove that. So lower bound means you will show that answer is a lower bound. Oh, it's one or two only. How though? You have to make it empty, right? So what do you do here? Okay, what do you do here in test case 3? How do you prove we can do it always in 2? I hope that's not correct. Really? Okay, it's one or two. It's one or two. I can see that too. Okay, it's one or two. Bad layer. Someone told about the bad thing, right? Finding. See, I saw your idea of finding that. Okay, see, I would have came to. I don't like the term intuition. I may remove you if you use intuition again. But yeah. So yeah, someone is telling bad layer. Yeah. Okay. Now I understand that. Now I can see that. Okay. If first half is less than or equals to second half, then you can do in one operation. Else you choose see, first half less than second half means this half is values are also less than, the values are also less than half of n, the values are also greater than half of n, right? You have to see this thing in like this. If you see this thing like this, okay, these are indices, let's say 1 2 up to so on n by 2 up to so on n. If first half is less than second half, you can do it in one operation, okay? But if is not less than second half, okay, why do you guys spoil the problem for me? Now we cannot know how the approach is very well, right? You can choose this first, you can choose this next, remove them, and then you can choose this, remove them. So the problem is done. Someone spoiled to me. It's either one or two operations. Why do you guys spoil? Like, I'm trying to solve the problem, right? Yeah, fine. So here one and even if it is one and two, they are lower bounds because you have to do at least one operation. In this case, one operation is not possible. You have to make it. See, minimization problem is nothing but lower bound is what I mean. Okay. Okay. Now I won't implement this. This is a stupid problem, right? So see, this diagram should be enough. So for one operation, all of them should be below, all of them should be above. Then you have it. maximum of this less than that. It's not about drawing the diagram, but it's about, I don't know how I could have came up here. I could have, but you have to guess sometimes. Even I thought it may not be possible. But then, yeah, with respect to values, see, if the values are less than half, you can remove the above values and below values, and then you can remove this. So what do I do? I will make the four groups, okay? Implementation. I'll make four groups. Let me just make it g of 2, 2, okay? hmm I'm implementing for the fun. G of I less than or equals to n, and P of I less than or equals to n by 2 dot pushback of I. Should we output indices or the values? I think it's the values, right? What happened? Okay, what happened? So now what we should output? I think I should output values. So what would I do? If g of 0, 0 equals to 0 or dot size, g of 0, 0 dot size equals to n by 2. So if this group is 0 or n by 2, then it's done. Okay. I don't think you get e solution elsewhere. Okay. That easily. Maybe Satyam can give you, but yeah. Now here, what should we do? I think we have to show the size too, right? So I less than or equals to n should be coming first. So this is the answer. Okay. So let's verify. So we got one operation which is two things done. Let's verify this one. We got one operation and then done. There should be two operations, right? See, two operations. First, 4 and 1 were removed. Wait, 4. Okay, I have to be careful here. We are always removing, outputting 0 things first, right? And 0 things will have I less than or equals to n by 2 first. How does 4 come here? So it means g of 0, 0 is being 4. How can that be? How can g of 0, 0 be 4? How can g of 0, 0 be 4? Because g of, it doesn't satisfy any of that. Oops. Fine, 2 comma 4 3 comma 1 done. So now we have to deal with f. Yeah, and then I made c plus 1 somewhere else, right? I made sure that c plus 1 will be somewhere else. I came back to that later. I made sure that c plus 1 will fall somewhere outside. You know what makes sure that? This makes sure that. I'm also fixing c plus 1's c's position with n minus 1 minus m. And then I'm reordering any other things. Okay. Is that fine, Akanksh? Okay, now f. Let's go for f. So let's read f. Maybe I won't solve it. Maybe I'll just give overall above. Oh, it's again counting. Seems counting. You're given an array. Yeah. It's if it is one operation's half of, how you came in between. You have to observe that if it is in two operations, you have to observe that what are the bad things. Bad things are something that lie less than half. See, if this is below all of them, okay, I'll make it better. If first half less than or second half, in other words, first half values less than or equals to n by 2. If you notice this one, now you can think about the diagram that I gave you. Okay, these things seems to be the outliers now on this thing. So you can remove those two and then you can remove these two and then you're done. Okay, this is the solution. I hope this diagram clarifies everything in the worst case. So yeah, you guys could have notified me before. So let's read the problem again. Okay, try your best again. You're given an array of length n. Let f of a comma I denote the number of indices j such that 1 less than or equals to j less than I, aj greater than ai. Is that an inversion? No, it is f of a comma I. For f of a comma I is number of things below before that above this value. Okay, let f of a be the set of indices I such that so having the maximum value of f of ai. So number of things above this, number of things above this, number of things above this. Some things have f of a is the maximum indices, number of indices that have this maximum value. You do not want f of a to consist of only one element, so you may perform the following operation any number of times. Let x be the minimum number of operations needed such so that. Why do they say any number of times and then say minimum number of operations needed so that f of modulus of. Why do they say you can perform any number of times and then say fine? I'm working at some other startup. Maybe that's the reason. Two ways are different if there exists an index j such that. Okay, bye. So, guys, let's try F now. Let's try to give our best. I'm very tired, but let's try to give our best logically. Since the number might be large, output this. Nope, I just joined. I cannot write. They want to hire, but then they're hiring aggressively. But I don't think I am good enough for them. But yeah, your wish. You can try to apply for them if you want. It's called One Mind. So LinkedIn. I don't know why this guy pops up all the time. I just joined this small startup called One Mind. Fuck was that? So yeah, we have to read the problem. F of a be the set of indices I such that having the maximum value is this. You do not want f of a to consist only one element. You may perform any number of operations. Select and swap. So you can swap them. You can swap values, but you don't want something like that. A less than or equals to, it's not a permutation for the first time. Okay. Let x be the number of operations needed such that you make that it can be proven that x is finite. So x is minimum number of operations needed. Find the number of ways to achieve in exactly x operations. So first problem is finding x. What is the minimum number of operations needed for that array? And then you have to count them. Number of swaps you can do. So again, it's a good problem. There is something nice here that shows you that this is the lower bound. And then you find, so you have to find lower bounds again. All minimization problems are about finding lower bounds, guys. See, if you show that, I cannot. go over all of my 1000 unaccepted LinkedIn requests and then find you, bro. It's difficult. Sorry. And I cannot help to, even if I found you. So, yeah, we have to think about this problem. You can do swaps. How do you come up with swaps and minimum number of operations for this thing? What happens in one operation? Only one inversion, only one index's value might change, right? In one operation, if something greater than comes before, if something smaller goes like that, in one operation, what happens is this will become minus 1. And this, okay, there is a swap happening, and then, so in one operation, there is a swap happening for f of a. And then what happens? The bigger value goes here, swap, and the smaller value will become minus 1. You have to make them 2. You have to make some size 2. The size can be anything. N is 10 power 6, so it's definitely a nice problem. How do you come up with the minimum number of operations? Yeah, Akanksh KH, that's a nice observation. Thanks for telling me. I have considered that after some time, and then I'm fixing C outside. I'm fixing C outside. See, that's why we got this additionally. So these are outside edges. I'm fixing C on them. So I fix it C now. I'm taking other than C, n minus 1 minus C. These many things, I'm reordering them. So C went outside. Very clearly, it went to n minus 1 minus m. Is that fine? Thanks for pointing it out. At least I think you're understanding it. Right. So now we have to again solve this problem. How can there be lower bounds? Like there are many f of a's. Any of them may become equal. Right. Okay, I have one doubt. Can we look at f of a instead of a? Is that possible? See, in A, only relative ordering matters, right? So what I'm telling is, okay, you have f of A's value, number of things before that. So is there a bijection? Think about that. If you know f of A values, can you come back to A? I mean, may not be exact A, but can you come back to A? That, yeah, it works, right? It works. C is outside, so you can come back with C. Because while going, you might have touched everything. Okay, while going to last edge, you might have touched everything, and then you come back in the same path. I'm making sure that it's not on the path, right? Damn, damn. So it's unsolved. Thanks for telling me that. So I have to add few more things now. I have to add few more things. Okay, I have to add few more things. No, I haven't calculated at least C. What I have calculated is just some part of equals to C, because so I think then calculating at least C is good, right? Can we calculate at least C? If we can calculate at least C, then we can subtract those two things. At least C and at least C minus C plus 1. So have we calculated at least C? I think if I go with my initial solution without fixing C outside, then what do I have? Then what do I have? And then we have to do C minus C plus 1, right? Remove this one. n minus of c minus 1. What does that mean? Okay, c minus 1 it just comes here. Okay, there is a path till c minus 1 here, and c can be anywhere. What does this guarantee? This guarantee greater than or equals to c. Greater than or equals to c implies that up to so on c minus 1 comes till here. So exactly c is exactly this. So I think this is good. Yeah, this is perfectly good. That's great. So we know it means to be greater than or equals to c perfectly, because that's what I have done initially. And then I thought, okay, it's at least c, right? So let me fix. But then I haven't done it right. I thought it should be outside, but it can be on the path before c plus 1 is a very good point. And then it became complicated now. But yeah, but we know exactly what it means by at least c. That's what I have computed in the beginning. So removing c plus 1 is great. So guys, join my groups. We have live stream groups. Join them. You can find it on posts. So now let's try to solve this problem too well. Okay. I'm asking, I'm asking, is f of capital F of A and F? Do we not need to worry about small f of A is my question. Okay, so let's take 1 2 1. What is capital F of A? 0 0. No, it's not enough because we cannot separate equal and less than, right? That's why it's not enough. If all the values are distinct, maybe, but now equal, we cannot separate equal from that. Okay, anyway, if you swap equal things, it doesn't change. If you swap bigger and smaller things, what happens? What happens? If you swap to adjacent bigger and smaller things, the smaller things, the first the values will get swapped, and then the smaller things value, if the bigger thing came before, the smaller things will value will increase by 1. If the smaller thing came before, the smaller thing's value will decrease by 1. You have to make them equal. Can we always do it in less number of operations? Can x is x something small? Think about that. You have 0 here, and then you have something big. If you have something small, okay, if you have 1, if you a of 2 greater than a of 1, answer is done. So this is correct solution, right? Maybe not. What was I made? So what do I do? So I'll make it answer times equals to -1, and then I'll do c plus plus, and then I'll again do dfs of 1 comma 1 comma 0. This would be the answer. So we are subtracting the previous answer, and then we are adding c plus 1's answer. Is that clear? Is that clear, Akansh? Do you think it's fine? Pa, 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 pa. So if a of 0 less than or equals to a of 1, then done. No, not exactly, because we are subtracting the. Oh, okay. I made a mistake again. So let's keep that positive. You may say again, this is not enough. Before you correct me, modulo has been corrected. Okay. A of 0 less than or equals to A of 1, then done. Both are 0, 0. So is it one swap? I don't think the problem is this easy. Am I doing something wrong? Am I understanding something wrong? Okay, okay, maximum value, right? I forgot that. So it's like, I'm tired, guys. I won't be doing that. I won't be doing this. You want to make two things have maximum. Let's look at one maximum. What does that mean? I'm tired. I'm ending the stream. I cannot do this. Bye. Maybe I'll solve it later. Maybe I'll stream it later, but I'm tired. My legs are hurting. Bye. You can think logically. Okay, what is maximum? This is maximum. Means nothing else has more things before than this thing has. Okay. So there cannot be something smaller after than that. That you can say. Maybe I'll try that. So what can you say? If I is maximum, you cannot have something smaller than this after this. This you can say. If you have something equal, then f of a is greater than 1. But this need not happen. Even if there was something greater, because you can see some things over here. Let's say there are 3 things over here, and then you have 1 here, 2 here. Both 1 is having max, 2 is having max, right? So the answer again here is, this is a good array for us. But the problem is, let's say, let's look at one thing. At least one maximum exists, because that's a maximum, right? Let's look at that one. Let this be that maximum. This has maximum number of things greater than that. Okay. There isn't anything smaller before that that has these many things greater than that. For each thing we have some number of things greater than that. There isn't something before that that's greater than that. It's not being that simple, but I'm ending the stream. Bye, you guys. Before ending, we have only 9 viewers. I wanted 50. Then I'll just end the stream and I'll do some work. Bye. It was on campus. Okay, I don't need any likes. I'm ending.